Hey gang, last lesson in chapter 9, which we'll spend a couple of days on because it is kind of tricky. 9-8, powers and roots of complex numbers. And a big part of this lesson is based on the theorem of this man, Abraham de Moivre. He's a French mathematician, although he ended up living in England, I think, because of some religious controversies. He actually ended up being a friend of Isaac Newton. He was largely self-taught in mathematics, I think, and became quite a phenom at it. Became a friend of Isaac Newton. He actually did a lot of tutoring, so he was always kind of a poor guy. He never really got rich. And he also supposedly earned some money by playing chess. Interesting to note also that he correctly predicted the day of his death based on how many more minutes he was sleeping each day. So an interesting guy, and he came up with a very, very powerful theorem that is probably the crux, I would say, of this whole chapter. And here it is, de Moivre's theorem. Notice we have a complex number, and this is in polar form, or sometimes we refer to this as trigonometric form. But now we're taking a power of it. Up to this point, we've looked at doing various mathematical operations with complex numbers like adding, subtracting, multiplying, dividing. Last lesson we looked at how we might multiply and divide them when they were in polar form, which we can also do when they are not in polar form. But today now we look at how to find powers and eventually roots of complex numbers. So this is huge. Notice what this theorem says. If you have a polar form complex number raised to a certain power, all we have to do is raise the r value to that same power, and then we have to multiply the angle by that power. So here's kind of an abbreviated form that we'll refer to quite a bit. R theta to the n equals r to the n, comma, n theta. And of course we could put this back in rectangular form if we want to as well. But very powerful and important theorem. Now what problems related to this? Alright, so our first one here is we have a complex number that's in polar form, 2 cosine 60 plus I sine 60. We want to take that to the third power. According to de Moivre's theorem, we should, whoa, what happened to my pen thickness here? I'm going to thicken that bugger up a little bit. So we would take 2 to the third power, so whatever that r value is, we'd raise it to that power, and then we would multiply that angle by the number as well. So 3 times 60. So we know that 2 to the third is 8, and 3 times 60 is 180. So that's my shortened version of this. So if I wanted to write this out, it would be 8 cosine 180 plus I sine 180. And I think I'll just write it like that. Cosine of 180 plus I times the sine of 180. And of course I could write this back in rectangular form or that a plus bi form fairly easily. So that's all it is. Take the r value to that power, multiply the angle by that power as well. That's de Moivre's theorem. And examples that are maybe a little bit more complicated than that. Alright, notice this one. Now the trouble with this is that this is not in polar form right now, is it? 1 plus I to the fifth. I think you can see the tediousness of having to multiply 1 plus I by itself 5 times. Remember, in multiplication we can only do 2 products at a time. We can't do all 5 at once. So let's see how we could use this de Moivre's theorem to help us out a bit. First thing I think I would do here is see if I could draw a little triangle diagram so I can get a feel for what's going on. Again, the 1 plus I would mean that I am going to go over 1 and up 1 like this. So I could label it as 1 and 1 like that. I would need to figure out what is this r value and what is this theta. Well, by now you probably realize that when you have a right triangle that has 2 legs that are the same, that we're going to have a 45-degree reference angle, and that r value there is simply going to be 1 times the square root of 2. So in polar form, and I'm just going to use my abbreviated polar form, we would have the square root of 2, comma, 45 degrees, like that. Now, when I take that to the fifth power, I'm going to change pen colors here a bit. So I want to do that now. I want to take the square root of 245 degrees, and I want to take that to the 5th power. So, according to de Moivre's theorem then, I would take the square root of 2, and I have to take all that to the 5th power, and then I would take 5 times 45 degrees. That's all there is to it. Now, a little bit trickier here, what is the square root of 2 to the 5th power? Well, the square root of 2, of course, times the square root of 2 is just plain 2, so we'd have 4 of those. So we'd have 4 times the square root of 2 is what we would end up with here. And you can multiply that out yourself. I'm kind of rushing through this a bit. And then 5 times 45 is what? 225 degrees, I think, right? 5 times 40 is 200. 5 times 5 is 25. So 225 degrees like that. That's kind of my abbreviated polar form answer. Now again, if I wanted to switch this back into that a plus bi form, which is what I had started with up here, again, that wouldn't be too bad, because I would have 4 times the square root of 2, that's my r value, times the cosine of 225 plus I times the sine of 225. And I would just fill in the things I know. Of course, 225 is down there in the 3rd quadrant. Cosine value there would have to be negative, so negative square root of 2 over 2. Sine of 225 would also be negative. Same value, negative square root of 2 over 2i actually. And if I do go ahead and distribute this, I'm going to change colors for emphasis here. Go ahead and distribute this, I would get 2 times 2, which I think is going to be 4. Check out my multiplying there. Next, actually going to be negative 4 minus, I'm going to get another negative 4 because it's the same value here, negative 4 minus 4i. Now, that was a little bit complicated perhaps, but I guarantee you it's much nicer to do it this way than to have to multiply this binomial by itself 5 times as we might normally have to do. So again, get it in polar form and then use de Moivre's theorem to help you out. Alright, only one more problem. This one might be a bit of a doozy perhaps. Notice it says we're going to try to find the 5th roots of negative 32. So in other words, I'm going to try to find a number that I can multiply by itself 5 times and get 32. Well, you probably already know maybe what one of them is. Maybe negative 2 is going to be one, because negative 2 to the 5th power will be negative 32. But kind of like we talked about before, there should be 5 of these 5th roots. If I was taking 4th roots, there should be 4. 6th roots, there should be 6, that type of thing. So I should be able to find 5 total values that when I multiply them by themselves 5 times, I get negative 32. Let's sketch out where this would actually be. Now, negative 32, this is a complex number, so negative 32 is actually going to be over here someplace. So when I write this, I'd like to write this in polar form here right away. And so do you see that in polar form, it's going to be 32, comma, and to get over there, I'm going to have to go 180 degrees like this. So that's the number I want to get to, and keep in mind what I'm looking for then is some particular r value and some particular theta value which I can raise to the 5th power, so I get that. Okay, well, let's keep going on and see if we can mess around with this. I'm going to change back to yellow. Now, according to de Moivre's theorem then, this should be r to the 5th and 5 theta. And of course I still have my same 32 and 180 degrees here. Now, when I have these two equal to each other, perhaps you see that I'm going to set the real parts equal to each other, and then I'm going to set the angles equal to each other. So first of all, I'm going to change colors here again. So do you see that I'm going to have r to the 5th equals 32. Those are the real parts, so to speak. And then I'm going to have 5 theta equaling 180 degrees. Now here's a tricky part here. I must tack on there plus multiples of 360. And the reason I need to do that is because I need to account for all these different roots. If I did not put that in there, I'd get one answer and it would be a right one, but there are 4 other ones then that I would be missing. Okay, so clearly over here I'm going to get that r equals 2. 2 to the 5th power is 32. Over here, a little trick here, I'm going to have to divide everything by 180. Oh, excuse me, I'm doing that wrong. Good thing I thought something looked a little fishy. I'm going to see if my eraser works here, and it does. That's good. I don't want to divide everything by 180, class. I want to divide everything here by 5. I want to get theta by itself. So notice I divide not only theta by that, but 180 and also but 360. So theta is going to be, got to get out my calculator here, figure out what is 180 divided by 5. And that's going to end up to be about 36, it looks like. And then I'm going to have multiples of 360 divided by 5, which is 72. All right, now I have everything I need here for me to write my final answer. Remember that there's going to be 5 of them. So my first one is going to be, maybe I'll get a different color here. How about that? My first one is going to be 2, 36. I'm just writing these in abbreviated polar form. My next one will be 2, but then I need to keep adding 72 to each one of my subsequent angles. So that's going to be 108, I think. My next one is going to be 2, then I need to add 72 again, and I end up with 180. Number 4 root is 2, and it's going to be 252. And lastly, 2, comma, and then 72 plus 250. 2 is, what, 324? Is that right? I think so. So there are my 5 roots of negative 32. Now again, I could write these back in a plus bi form if I just expanded that out a bit, and we'll practice on that in class certainly. So hopefully you have that de Moivre's theorem down in your notes and have kind of followed along with these examples. Again, this is fairly tough. If you're not sure right now, don't worry. We'll get it the next couple days. Thanks for watching, and we'll see you guys in class.